Hello. Today we're going to be having a look at the binomial distribution. This is one of the more important distributions that you will cover as part of the A-level maths syllabus. There's this one and the normal distribution, which are our sort of two key distributions that you need to know. This is an example of a discrete distribution, so one that can take a whole number of values, and I'm going to sort of explain how it works, explain its links to some of the things from GCSE, some of the things that you've seen before, and also come back and look at that nature of it being a discrete distribution and sort of what that means in terms of the numbers here. So the first thing we're going to have a look at is we're going to go back to that idea of dropping coins like we were looking at when Mr. Crofts came in to do some recording. We were dropping 4 coins then. We're just going to look at dropping 3 coins here today because of the ease of in terms of the example. So if I drop 3 coins and we're going to record whether they are a head or not. We're interested how many heads there are, so we've got this statement here, let x be the random variable representing the number of heads. Essentially what we're saying here is that this large X represents the number of heads that we could have. So here I've got 3 tails, and here is an example of where I've got 1 head and 2 tails. I don't know if that's maybe a bit too dark for you to see. Is that a little bit better? There we go. So we've got 2 tails and 1 head. I could have 2 heads, 1 tail, and so on. Now we looked at this idea of dropping and flipping coins last time, and we found that there were several different ways of getting, say, 2 heads, but the order didn't really matter to us if we weren't looking at the idea of, say, placing in a race or something like that. Now, this idea of combinations and the number of different ways that we could get 2 heads, or 1 head, and so on. We're going to write down sort of the examples of the different ways we could combine these coins and the outcomes to get these different things. So I'm just going to move these to one side. How could we get 0 heads? Well, we could get tail, tail, tail. We've seen that before. How could we get 1 head? Well, we could get head first and follow that up with 2 tails. Because remember, I've got my 3 coins, so head on the first, tail on the other 2. I could also get a head in the middle, so the second coin could be a head, or I could have the 3rd coin being a head. So here, as you can already see, it's much more likely that I get 1 head than I get no heads. It's very, very rare in this sort of sense for us to only get no heads, to drop these 3 coins and get no heads. So if we look at 2 heads, it's just going to be sort of the mirror image of this. So I could get, say, 2 heads and a tail. So this one here is a mirror of that one, where the tails have become 2 heads and the head has become a tail. I could move one of those heads along one, so swap these 2 round, so I could have a head and then a tail and then a head. That's 2 heads. Again, that one's a mirror image of that one. And then finally, I could have a tail and 2 heads, so move that final head along one. So I could have here tail, head, head, and that one's a mirror image of that one, isn't it, where the head becomes a tail and the 2 tails there become 2 heads. And then finally, the 3 heads option is just head, head, head. So as you can see, getting 1 head or getting 2 heads is far more common than getting no heads or getting 3 heads. Now if we were to fill this in terms of our probability distribution function, this is the kind of thing that we saw last time. So here we've got our outcomes across the top, we've got our probabilities down here, and you've been working on some of these in the exercises recently. So if we fill this in, here I've got 1 out of 1, 2, 3, 4, 5, 6, 7, 8. So here I've got 1 out of 8, and 8th is my probability for getting no heads. For getting 1 head, there are 3 options out of the 8 in total, so that's 3 out of 8. Similarly for 2 heads, it's 3 out of 8. And then for 3 heads, again, it's 1 out of 8. So here we can complete ourselves a probability distribution function by considering sort of the theoretical outcomes and what happens. Now that's fine and well if I've only got 3 coins, because 3 is quite a low number, and this was reasonably easy to do with just 3 coins. We did it with 4 coins, we thought about what that would look like, and we got the pattern 1, 4, 6, 4, 1 as our number of outcomes, and we sort of linked that up and related that to the 4th row of Pascal's triangle. Now, there is another way of approaching this, a numerical way of approaching this, which will obviously make things easier, especially if this number gets bigger. If we start considering sample sizes not of 3, but of maybe 10 or 20 or 100 or more. When you're thinking about things like medical trials, we're not thinking about, I'm testing this drug on 3 patients. You're testing it on hundreds of people, and you're working with probabilities of it curing somebody or not curing somebody. So we want to be able to think about how we can do this numerically, so that we're not restricted to just this sort of theoretical side of things. So if I just move this down here, so we've got the table, but we've got these 4 probabilities that we're going to work out. Now, we're going to get an answer of an 1/8 for this, but I just want to show you sort of where this comes from in terms of our structure. So there's only one way of getting getting no heads, so that's 3 tails. There's only one way, so I've got 1 multiplied by, and now it's going to be the probability of a half, because that there is the probability of getting a head, to the power of 0, because I don't want any heads, multiplied by a half to the power of 3, because this is the probability of getting a tail, and I want 3 tails. So there's one way of getting no heads, it's probability of a head, and then 3 tails, that's the probability of a tail. So it's probability of a tail times probability of a tail times probability of a tail. Now I know what you're thinking, like, what is he doing? Where are all these numbers coming from? But if we take a quick look at this, let me just pull the visualizer up here a little bit so you can see it. This here is the probability tree diagram that represents this situation. So here I've got 3 heads, there's 2 heads there, 2 heads there, 1 head there, and so on. The strand that we're looking at the moment, this idea of getting no heads, is this bottom set of branches here. Now when you're multiplying, when you're working with a probability tree diagram, you'll remember from GCSE that you multiply the probabilities on each of the branches. Well, the probability of getting a tail is a half. The probability of getting a tail is a half. The probability of getting a tail is a half. So a half multiplied by a half multiplied by a half. So that's a half cubed, which is exactly what we've got in terms of numerically. Now again, as you can imagine, if I were to extend this to not being just 3, 1 coin, 2 coin, 3 coins, if I were to extend this to be hundreds of patients on, say, a drugs trial, then this tree diagram is going to get really sort of unwieldy and large. So we do need to have this numerical way of approaching it. So a half times a half times a half, like on a tree diagram, that's exactly what we've got here. A half times a half times a half. Let me just zoom back in on that so you can see it easier. So half times a half times a half. This here kind of is a placeholder because it's going to help me with the next one. We know that anything to the power of 0 is 1, so actually we could get away with not including that at all. And in the same way that I know that here I've only got one way of getting no heads, then I could again get away with not having that. But in the next one we've got 3 ways of getting 1 head, and we've got probability of a head, I want 1 of them. Probability of a tail, I want 2 tails. And that's exactly the same if you think back to your tree diagram. So one of the branches has got heads on it, probability is a half. 2 of the branches has got tails on it, so the probability is still a half. Now if we were to work these things out, 1 times 1 times, well, half cubed is an 1/8, so that matches up with the probability that we got by thinking about it theoretically. Here I've got a half times by a half times by a half, so that's an 1/8, times by 3 is 3/8. So again, that is the same as the probability that is here when we were doing this theoretically, and we can carry on in the same way. So 3 times by probability of a head is a half. How many heads do I want? It says here I want 2, so it's going to be to the power of 2. And then probability of a half, this is for tails, and I want 1 of them. So a half times a half times a half is an 1/8, times by 3 is 3/8. And then finally I want 1 lot of a half to the power of 3, so that's probability of a head, I want 3 of them, times by probability of a tail, I want 0 of them. So again, this is a placeholder, isn't it, because a half to the power of 0 is 1. But what this does is it does help us to come up with a generic way of writing this. So a generic approach that we can use to work out these probabilities no matter what the situation. Here this is a fairly dull and straightforward sort of set up for a problem because it's coins, the probabilities of heads and tails are the same. I've only got 3 of them. It's not very illuminating, so we're going to have a look at another example where it's easier to work with. Now, you might notice here 1, 3, 3, 1, and as we looked at in class 1, 4, 6, 4, 1, when we had 4 coins, these are rows from Pascal's triangle. And as we discussed in the previous video, those rows of Pascal's triangle, they are just the combinations. So things like here, this is just the number 3 is 3C1. 3 choose 1 will give me 3. 3 choose 0 will give me 1. 3 choose 2 will give me 3, and then 3 choose 3 will give me 1. So we're going to use this fact here and the practice that you've been getting in the previous exercises to help us with this next question. So I'm just going to shuffle that down a bit. There we go. Right, so this one here, we're going to consider a spinner with 5 equally likely sections. They're coloured red and blue. So 2 of them are red, 3 of them are blue. Here we're going to say that the random variable x is landing on a red section. So for us, success is landing on a red section. So I want the probability of getting, if I roll this spin this 4 times, so it says here we spin the spinner 4 times, and we're going to complete this table. So if I spin the spinner 4 times, what's the probability of getting no reds? Red is my success. So here what we're going to do, if I want to work out the probability of getting, so x equals 0, how many times am I spinning it? I'm spinning it 4 times, so it's going to be 4, choose, and how many do I want to be red? I want 0, none of them to be red, so this is going to be 4, choose 0. Now hopefully you should realise that there's only one way of getting none of them 0, so 4 choose 0 should come out as 1, and you can check that on your calculator, it does come out as 1. Multiplied by, now we want the probability of getting a red. So what is the probability of getting a red here? Well, 2 of them are red, each of them are equally likely sections, and there are 5 sections in total, so it's 2 out of 5. So I'm going to put 2/5. You may put 0.4 if you wish, but I like fractions. So 4 choose 0 times by 2/5 to the power of 0. I don't want to get any reds. Multiplied by 3/5. So this here is the probability of not getting a red. In this case, that means getting a blue. So probability of getting a red, I want none of them. Probability of not getting a red, I want 4 of them. So 4 outcomes that are not red, 0 outcomes that are red, and then I've got my number of combinations, so 4 choose 0. And then we can work that out. Try my calculator. So if we work that out on our calculator here, I'm just going to pop that there so we can see. So we're going to have, turn it on, so we've got 4 choose 0 multiplied by fraction 2/5 to the power of 0 times by fraction 3/5 to the power of 4. And I know what you're thinking, what's the point, sir? 4 choose 0 is just going to give me 1, 2/5 to the power of 0 is just going to give me 1. Why don't I just type this in? And you can, once you get to a point of not really needing to use this structure every single time, you can, take a few shortcuts. But now, when you're starting out with this, I would definitely use this structure every time. Number of combinations, probability of success to the power of the number of successes, probability of failure to the power of number of failure. So if we do that, we get 81 over 625. So I'm going to fill that in here. So 81 over 625. So not very likely. Next one then. Probability that x equals 1. So it's going to be number of combinations. So that's 4, and I'm choosing 1. So 4 choose 1. And then it's going to be 2/5. So that's the probability of success, getting a red. How many successes do I want? I want 1. Multiplied by 3/5. That's the probability of failure, that's not getting a red. And how many do I want? I want 3 of those. So again, we can then just go onto our calculator. I'm just actually going to go through and edit this, so delete, put 1 in there, and go across to this one, delete, put a 1 in there, and go across to this one, delete, and reduce that to 3 equals 216 over 625. So 216 over 625. And then we can carry on with that, as usual. So probability x equals 2. So it's going to be 4 choose 2. 2 is the number of reds that I want. Multiplied by probability of red is 2/5. I want 2 of those. Probability of not red is 3/5, and I want 2 of those. I'm not going to fill the rest of this table in because that would just take up time. It's a bit of a wasted exercise. What I'm actually going to do is I'm going to look at some extra notation you might see, what it means, and have a look at another example alongside that extra notation. So the extra notation that you might see, you might come across, you will need to use or will need to become familiar with is the notation that tells you the important things about a binomial distribution. So here we're testing a drug with a success rate of 92%, so that's a probability of 0.92, and it's tested on 10 people. So if I were doing a tree diagram here, I'd have 10 sets of branches going all the way along. It's going to be very complicated. No point trying to draw that kind of thing out. We need to make sure that we're using our numerical methods for this. So the notation you might see is the following. You might see x and then this squiggle, this is called a tilde, so x tilde b, and then you get some values. So I'm going to write n and p there. So n here stands for the number of trials, and the p here is the probability of success. So in this particular example, we've got x, our random variable x here. The random variable x is how many people are cured. So here x is binomially distributed with number of trials 10 and probability 0.92. Now we've gone through this with one major assumption in mind, and that was prevalent in the previous two questions, and it's the same in this one, and that is that the probability of success is the same from trial to trial, from participant to participant. So this drug has a success rate of 92% for every single person in this trial. Now there's arguments then about how likely that is in the real world and whether the binomial distribution here would be an adequate fit, and that's another question entirely. For now, we're making that broad assumption that each of these 10 people, the drug has a success rate of 92%. So, number of people cured is binomially distributed. I'm looking at a trial of 10 people, and I've got 0.92 or a 92% success rate. The question here is to find the probability that it cures at least 8 of them. So I want the probability that x is at least 8, so it's greater than or equal to 8. So we're going to consider in a moment what that means in terms of the probabilities that I need to work out. So I'm just going to shuffle this down. I'm going to rewrite my important piece of information because this is the entire question here condensed. I don't need any of the other spiel. I don't need to know that it's a drug trial. I don't need to know that 92% represents the drug's success rate or anything like that. The only information I need is how many trials there are in total, probability of success, and then this here is the question. This is what I want. So here the probability that x is greater than or equal to 8, that is the probability that x equals 8, and the probability that x equals 9, and the probability that x equals 10. So here I'm interested, shuffle that along, I'm interested in it being successful for 8 people or 9 people or 10 people, and I want to add these three things together. There's an equal sign. I want to add these three things together. So I'm going to work these things out individually, and we're going to use that same structure. So here, the probability that x equals 8. Right, so we had our combinations first, didn't we? So we had 10 choose 8. So this here is 10 choose 8 multiplied by the probability of success, 0.92. How many successes do I want? I want 8 of them, so the power here is going to be 8, times by the probability of failure. Now, we're not given that, but it's easy to work out. It's 0.08 in this instance, because if success is 0.92, failure must be 0.08, because these two probabilities here have to add up to 1. So, if I've got 8 successes, how many failures are there? We've got 2, because 8 add 2 gives me the total number of trials, which is 10. So let's work that out. It's the same way for probability that x equals 9, so we'll do that one, and then we'll start working these out. So 10 choose 9, want 9 successes, multiplied by probability of success, 0.92, want 9 successes, so the power is 9, multiplied by 0.08 to the power of 1, because this is how many failures we want. And finally, x equals 10. We're going to have 10, choose 10. If you're thinking carefully about this, you should know that that is 1. 0.92 to the power of 10. Number of successes is 10, probability of success is 0.92. Multiplied by 0.08 is probability of failure to the power of 0, no failures. Okay, and then we can work out what these probabilities are individually and add them together. So I'm going to do that. 10, choose 8, multiplied by 0.92 to the power of 8, multiplied by 0.08 to the power of 2. So I get this here as 0.147807 ... Next one is the same, so we're going to do 10 choose 9 multiplied by 0.92 to the power of 9 multiplied by 0.08 to the power of 1. Here we're going to get 0.377729 ... And then the final one, this will be 10 choose 10 multiplied by 0.92 to the power of 10 multiplied by 0.08 to the power of 0 at 0.434388 ... Now, as we said before, if I want to find the probability that this cures at least 8 of them, so that's greater than or equal to 8, so 8 is included because it said at least 8, then I need to add together these three things. So we're going to add these three together to get our probability that x is greater than or equal to 8. So 0.377729, 0.147847. So here we get 0.9599, and that there is the 4 significant figures, which you will find. Oh, sorry, move that up a bit. Which you will find is the standard degree of accuracy that most examiners will look for, even if they're not asking for it outright. 4 significant figures for probability is generally accepted. Now, one last thing just before I finish is I would like to show you, just by highlighting where a lot of these numbers and things come from, because there is quite a lot of information in this video. You might want to just watch things back just to make sure that you understand where all these things come from. Like I said, the only key information you need here is this stuff from the questions. So there I've got 10 is the number of trials. Notice that that then is prevalent throughout the whole thing. That's the number that I am choosing from. And then here I've got my probability of success, 0.92, and again that is prevalent in this here, in my sort of standard structure too. My 8 matches up with my 8 there and my 8 there. My 9 matches up with my 9 there and my 9 there. My 10 matches up with the 10 there and the 10 there. So the same structure all the time. It's coming from these things here, there, and here, and then it's coming from the individual probabilities that you're trying to find. So probability of having 8 successes, 9 successes, 10 successes. So 8, 9, 10, 8, 9, 10. Noticing here that these two numbers always add up to give me the total here. So 9 add 1 gives me 10, 10 add 0 gives me 10, and these two probabilities always add up to 1. So 0.92, probability of failure 0.08. So they add up to 1, they add up to 1, they add up to 1. So it's certainly worth giving a couple of these questions a try. They're on page 189, so that's exercise 2.4, and 190, so that's exercise 2.5. Have a go at some questions. If you've got any questions at all, drop a question in the WhatsApp group, or put a comment on the video, or send me an email, and I'm quite happy to run through some work solutions and then email those through to you.